Hello friends, welcome back to my channel, and in this video we will learn how to perform Archard wear analysis between the two parts of hip implant, which is head and this is stem, and we will learn how to perform wear analysis among these two bodies of hip implant. So first we will go to Ansys Workbench, and I will create here a static structural module, and there are already three files which I have done which I have prepared for the analysis, and we will copy this engineering data to this tab. In engineering data I have already given the properties of stainless steel. You can see here all these properties: alumina and cobalt, chromium and titanium. So there are four materials which I have already predefined for my analysis, and these materials will be used in our analysis. So I will close here, and I will also copy this geometry here, and now I will go to model. It will take some time. And for Archard wear analysis, you should know that what is Archard wear. So the Archard wear, this is my paper in which I have given all this formulas. Uh, this is my paper, and for Archard wear, Archard wear, what is Archard wear? Archard wear, linear wear is calculated with this formula, with this formula, LW equals to KW into PS into S, where LW is linear wear and KW is wear coefficient, and P is sliding pressure, and contact pressure, and S is sliding distance. So for calculating the linear wear between two parts, we need to know about wear coefficient KW, and P is contact pressure, and S is sliding speed. Sliding S is sliding distance. Okay. So you know that for calculating linear wear among two parts, we need uh, three parts: KW into P into S. KW is wear factor or wear coefficient, P is contact pressure, and S is sliding distance. So what is KW? Wear coefficient. Wear coefficient in this paper I have also given the wear coefficient between two materials. The wear coefficient between two materials is between cobalt, chromium, molybdenum and alumina. The wear coefficient of friction is 0.27, and wear coefficient is 2.4 into 10 to the power minus 8. Between alumina and titanium, the coefficient of friction is 0.41, and the wear coefficient is 58.2 into 10 to the power minus 8. And similarly, between cobalt, chromium, molybdenum and titanium 6Al4V, the coefficient of friction is 0.53, and the wear coefficient is 2.97 and 10 to the power minus 8. So initially we need to know KW, into which we will multiply contact pressure and sliding distance, which we will get from the analysis. So we will go into the Ansys Workbench tab, and you can see that this is the geometry of the hip implant. into which we will find the wear between these two parts. There are two parts. This is called the hip implant head and this is called the hip implant stem, and we will calculate the wear between these two parts, the neck of the stem and the hole of the head. So we will go to first of all this geometry and we will apply some material here. We will assign the hip stem with titanium material and the sphere with the alumina material. So if you want to know the properties of titanium, you can just click here and you will know that the properties of um, alumina such as density, tensile yield strength, tensile ultimate strength, and Young modulus. These are given here. So similarly, you can find the properties of cobalt, chromium, 316L stainless steel, and alumina as well. So this is the material type. We will minimize this, and you know the geometry very well. This is hip stem, and this is sphere, and we will create a additional coordinate here. This global coordinate is here, and we need to apply the loading force into the head. So we need to create an additional coordinate system here, and we will click this geometry head to create this coordinate system. This coordinate system has the value of zx and y here. You can see that the global coordinate system is here. So we will apply the forces on new coordinate system. This is in the head, and now I will keep the connections. I will define the connections. The contact region, you can see that clearly here. You can see clearly here that the contact body is shown here, and you can see here this is the contact body. This is the contact body in which we will perform wear analysis, Archard wear analysis. So you need to know about this surface area as well. You need to know about this surface area as well for calculating the linear wear. You need to know kw into p into s, wear coefficient, contact pressure, and sliding distance. Where if we want to know the volumetric wear, we need to know the linear wear Lw and A as well. A, what is A? This is the contact area. This is the contact area between these two bodies. This is which is head and stem. So in the red color, you can see the contact area of the neck. So how you will calculate this contact area? You will just calculate the first area as well. First area at first. You will use the formula pi into pi r square, where r is the radius of this, upper part of the body. And for this portion, you will multiply pi d into this length of the neck. So the length into the pi d will give you the area of this across body, and the upper area you will know by just using the formula pi r square. Okay, so we will define the contact region, and here we will set this type to frictional, and we will give here the coefficient of friction between titanium and alumina is titanium and alumina is 0.41. So we will give here the coefficient of friction is 0.41. Okay, and now you are done. And in the mesh, you will insert a method, and you will select the geometry, control upper body and control lower body, apply, and you will give here method tetrahedrons patch conforming method, and you will give here size of 1, select two bodies 1 mm, and just update mesh. It is taking time. So you can see that the meshing is done, and you can see how fine this is. And now we will go to static structural. We will apply some supports here, fixed support, where at the bottom of this body I will select this face and third face. Okay, so we have given fixed support here, and I will also create a force at the head of this sphere. So I will go to force, and I will select the geometry as this upper face of this head. I will apply here, and I will go to components here, and I will select here the new coordinate system here, and I will give a load of minus 750 Newton of the force to the z direction, and you can see this there is the force working at the minus z direction. Okay, and now go to solution, and you can just calculate equivalent 1 misses stresses, deformation total, and equivalent 1 misses strain. These are all the formalities, and not very much needed for calculating Archard wear, but you absolutely need to create here a contact tool analysis, and in this I will insert pressure, which is contact pressure, and insert sliding distance, and I will go to solve and wait for the analysis. This will take. So friends, the analysis has been done, and you can see that the contact pressure is known to us, and this is 34.945 megapascal. This is contact pressure, and below you can see the sliding distance between these two parts, which is head and stem. This is 0.00438803 maximum. So in this way we have known the contact pressure and sliding distance between these two sliding parts, head and stem of the hip implant. And now we will go to this formula for calculating the linear wear, which is kw into p into s, wear factor or wear coefficient between the alumina and titanium. Alumina and titanium, which is 58.2 into 10 to the power minus 8, and we will multiply the contact pressure P with this 34.945 megapascal, and again we will multiply the sliding distance S with this 0.0043803, and in this way we will got to know about the linear wear between the sliding parts of the hip implant, which is head and stem. And similarly we can calculate the volumetric wear, which is VW, which is equal to LW into A. And what is A? I have already calculated here. The value of A is 1420.5925 mm square. 1420.5925 mm square is the surface area, head trunnion interacting surface area. The contact area is the contact area is the contact area is what you can see in the red portion. You can calculate as well. I have shown earlier the formula for calculating this contact area. So the area is what? 1420.5925 multiplied by contact pressure and sliding distance. So the contact area 1420.5925 will be multiplied with the linear wear LW. Then we will get the value of volumetric wear, and this is the case of Archard wear analysis. So you can see here as well, I have given the summary of result in my uh, paper, which is namely as wear and fatigue behavior investigation of hip implant head stem interface using finite element analysis. So you can search this topic in the Google, and you will find the free copy in ResearchGate, in which I have uploaded a free copy there, and you will see all the results of wear analysis among different materials such as cobalt, chromium, molybdenum, alumina, titanium, 6Al, 4V, alumina, and between these two materials as well. So you can see that there are contact pressure. This is the value of these are the values of contact pressure, and these are the values of sliding distances for different analysis, and this is the linear wear LW, and by multiplying the contact area between the two contact bodies with linear wear, we will get the volumetric wear. So in this way we have calculated the wear analysis of Archard wear analysis of this hip implant geometry. So hope you understand the way in which we have calculated the wear analysis of hip implant geometry, and you can also check my paper as well. You can fully read this article as well, which is freely available in the ResearchGate. So, for knowing better about the more complex things involved in the papers, so that's all. Thank you very much for being at the end, and I will upload a video on how to calculate fatigue analysis as well in the later of my videos. So please like this video, subscribe to my channel, and share as well. Thank you so much.